Hi, my name is Florian Hildebrandt from the University of Hamburg, and I will be talking about non-parametric calibration for stochastic reaction-diffusion equations based on discrete observations. The results presented here are based on joint work with Matthias Traps. So the model we are considering is the solution to a reaction-diffusion equation. So we're taking a look at a process of time and space, where in this case here space is given by the unit interval. And it is the solution to this semi-linear stochastic partial differential equation, where the time derivative is supposed to match a diffusion component with diffusivity parameter theta, a reaction term, which is given by a usually nonlinear reaction function f, and a noise process that is driving the equation. And this is supposed to be a space-time wide noise with a multiplicative constant sigma in front of it. When you set f equal to 0, you end up with just the usual stochastic heat equation. And from a statistical point of view, the natural question to ask here is how the single components of this equation can be estimated based on some kind of observation that we can derive from the solution process. And these kind of questions have already been asked in the literature. So the vast majority of literature on statistics for stochastic partial differential equations deals with the linear equations. So that would correspond here to the case where f is equal to 0. And there are different sorts of functional and also discrete observations have been analyzed. More recently, there have been some works on diffusivity estimation for semilinear SPDEs when functional observations are available. And what I will be talking today about will be the case of discrete observations in time and space. And for this particular equation, we will be estimating both the diffusivity and the volatility parameter and the function f in a non-parametric way. The solution to the stochastic reaction-diffusion equation can be written down in terms of this variation of constants formula. Here S always denotes the semi-group generated by this differential operator. And we have the following structure. We have a semi-group applied to the initial condition. Then we have a stochastic convolution. And then we have a convolution with the semi-group and the function f applied to the process. And when f is not present, then this whole term here vanishes. And you see that we have a closed form solution in this case. As you can imagine, when there is no closed form solution, things get much more complicated. And of this process, we assume to be given discrete observations in time and space. So we're taking a look at a grid of observation, which are depicted here in this plot. The observations are represented by the red dots, and they lie on some rectangle in space and time. Capital T denotes the time horizon, and we assume to be given n observations in time and m observations in space. In both coordinates, we assume equidistant observations. So the temporal time lag is denoted by a capital delta, and the spatial time lag by lowercase delta. Both are assumed to tend to 0. The time horizon may be either fixed or also go to infinity. And since both these values are assumed to tend to 0, we have high frequency observations both in time and space. And furthermore, the total number of observations is given by m times n. So first of all, I would like to talk about estimation of the two parameters of the volatility and the diffusivity. In the linear case, that problem has already been addressed in the literature. And there it was found that power variation techniques are an appropriate tool for estimating the parameters. Power variations are a tool that is very well understood for finite dimensional processes, but it can also be applied here. One particular result I would like to mention is that of quadratic variations based on double increments. So double increments are these kind of objects. So it's space increments of time increments, or equivalently time increments of space increments. And they have to be chosen in such a way that the difference between the 2 points in space is of the same order of magnitude as the square root of the distance in time. So we are not necessarily building our double increments from neighboring observations in time and space, but there may be some values here between L and K and also between J and I. And when you look at the quadratic variation based on those increments, you find that you can estimate the two parameters at a rate of convergence, which is given by this expression. And as you can see, it hinges on the interplay between the temporal and the spatial frequency, and it also involves the time horizon. And when this parabolic scaling here is present for the observations, that means when you can actually build your double increments with neighboring observations, so neighboring in space and neighboring in time, then this is the same as the parametric rate of convergence, so given by the total number of observations to the -1/2. When the scaling is not present, you get something larger, but in any case, it was shown that this rate is optimal. And what we have found out now is that these double increments estimators can also be used when f is not equal to 0, so when we're having a proper reaction diffusion equation. So in this case, it can be said that the double increments estimator for the two parameters is robust with respect to the perturbation f, and we achieve the same rate of convergence as before, and thus we also have a rate optimal estimator for reaction diffusion equations. Just a few words on the proof. So this is a technique that is often applied when dealing with semi-linear stochastic partial differential equations. So you take the solution and split it into a process which corresponds to the solution in case f equals 0. And the other part is just the remaining part. And then you do a Hilde analysis of the, or an analysis of the Hilde regularity of the two processes. And you find that the regularity of n is much better than that of x0. And that is why n does not contribute a lot to the quadratic variation and can thus be considered negligible. So secondly, I would like to address non-parametric estimation of the reaction function. And here we have used a similar approach as a non-parametric drift estimation for finite dimensional stochastic differential equations. And yeah, as in the latter case, the idea is to use your observations to set up a regression model. And this works as follows. So as a response variable, we take the time increment of the process, which is corrected with respect to the semigroup. And then when you're doing an expansion of this object, you find that it looks like f at xti, plus a term that becomes small asymptotically, plus a term that can be interpreted as stochastic noise. So this is actually exactly what is also done in the finite dimensional setting, except there it is not necessary to correct with respect to a semigroup, but you can just use the usual time increments. So there's a problem here, and that is that this object is not observable in our discrete observation scheme, because in order to be able to compute it, you need knowledge about the whole spatial process at time ti. And yeah, we have no access to that. And that is why we have to replace this object by some approximation, which only depends on the discrete observations. And that is denoted here by S hat. So now we are ready to give the definition of our estimator. So we're taking a look at some compact set A on which we want to estimate the function. We're considering an appropriate sequence of subspaces of L2 of A with growing dimension. And then the estimator for f is defined as the function in Sm that is the best fit to our regression type decomposition in the least squares sense. And for this estimator, we have derived an oracle inequality. Before presenting the inequality, I would like to give some some assumptions that we needed to impose. So first of all, in order to get a result for a large class of functions f, we had to require that the time horizon tends to infinity. Secondly, we needed to ensure some sort of ergodicity for the process to be bounded in some sense. And for this, this was done here by requiring that minus f grows at least linear at infinity. As I already told you, we needed to do some approximation of the space continuous model. And that means that we may not be too far away from continuity in space. So this results in this condition here that the number of spatial observations must be larger than delta squared. Finally, for the approximation spaces, you can take one of the usual choices. So trigonometric or wavelet basis work, and also piecewise polynomials are fine. And based on these and a few more technical assumptions, we were able to derive this oracle inequality for the L2 difference between the estimated function and the true function. And it has the following structure. So we have a bias term that tells you how well the function f can be approximated by a function in Sm. We have a variance part that is growing in the dimension of the approximation spaces and decreasing in the time. And then we have some remainder terms which come from the different approximation steps in the regression decomposition. And these first two terms, so the bias and the variance terms, are exactly the ones that you would also see in the finite dimensional case of drift estimation in stochastic differential equations. The remainder terms are larger than what you would get in the other case. Okay, so in order to be able to compute the estimator, you need to be able to choose an appropriate value for m, that is for the dimension of the approximation space. And that can also be done here in an adaptive way via a model selection approach. In particular, when we assume that these remainder terms are negligible, which can be achieved by assuming this condition, then the estimator achieves the usual non-parametric rate of convergence, which is given by this expression, which involves the regularity parameter alpha, and alpha describes the regularity of f in the sequence of approximation spaces that you are considering. So all in all, we have estimated both sigma and theta now, and also the reaction function f. And by doing so, we have achieved a complete calibration of the stochastic reaction diffusion equations. So here are some references, including the preprint that I have just been talking about. And thanks a lot for listening.